Now that we have these first four rules, we're going to try to use them to sketch a curve here. So we want to figure out everything there is to know about how the graph of this function looks. Because this is a preview of something that we're going to be doing later in the semester, when we're going to be doing some very applied real-world problems called optimization problems, where we're trying to find the best way of doing something. So maybe the way that uses the least amount of time. So you have some function, you have its graph, you want to find the lowest point on the graph. In other words, you want to find when the graph changes from decreasing to increasing. Calculus will let us do that. Maybe you want to find the most profitable way of doing something. You have some graph of your profit function, and you want to find out when it gets to the highest point. That's going to be when the graph goes from increasing to decreasing. Calculus will let us answer all of these very useful real-world questions. So let's start with this function here. Find the roots. This is not a calculus question. This just means where does this function cross the x-axis. So this means we just look for where y is 0. And now this might take you back to week 2, when we talked about how we would need to solve equations like this frequently. Here's the first case. And what did we decide there? It would be a really good idea to do something and a really bad idea to do something else. The really good idea was factoring. The really bad idea was dividing. If you now divide both sides by x to the 4th, you're going to lose one of the answers. So let's not do that. Instead, let's factor out an x to the 4th. And then we have 9 minus x squared. And now we're back in that situation we talked about in week 2. When we have the product of two real numbers being 0, that means that one of those real numbers, so we use this symbol for implies. This implies that either x to the 4th is 0 or 9 minus x squared is 0. And so what will make x to the 4th 0? X will be 0. This is like saying x squared equals 9. We've talked about that one before. That means x is either 3 or negative 3. All right, so there was nothing calculus about that. That's just, those are the three places where the graph is going to touch the x-axis. Now let's do some calculus. Where is f increasing? Where is f decreasing? Who knows? Just looking at this function, I have no idea where that thing is increasing and decreasing. Calculus will let us figure this out, though. We know that a function is increasing when its derivative is what? When its derivative is positive. And we know that a function is decreasing when its derivative is what? That's when its derivative is negative. So if we can find the derivative of this function and determine where it's positive and negative, we'll have answered these two questions using the power of calculus. So let's start with the derivative, f prime. So I've got my 9x to the 4th. That's our constant multiple rule and our power rule. So the 9 stays according to the constant multiple rule, and the 4 comes down. 9 times 4 gives us 36. And then we reduce the exponent by 1. We use our sum rule combined with our constant multiple rule to think about this as a plus a negative 1. And then we do 6x to the 5th. And now maybe once upon a time, people used to solve inequalities like this. You used to say, like, set this greater than 0 and somehow do a really messy thing and try to figure out where it's greater than 0 and where it's less than 0. I don't think they even teach that anymore. It's really hard to do. So we're not going to try to do that as a first go. We're just going to try to find out where this thing might be changing from positive to negative. And since this is a nice continuous function, it's just a polynomial, and polynomials don't have any jumps or any holes or asymptotes. The only way that a polynomial can change from positive to negative or negative to positive is by going through what number? By going through 0. So if I set this equal to 0, I'm going to find the places where this might be changing from positive to negative. And as we've said, f prime going from positive to negative is the same as f going from increasing to decreasing. So that's what we need to know. So we're setting this equal to 0. What do you think? Factor or divide? Let's factor it. So what can we factor out of both these terms? I see a 6x cubed. And I see I've got a 6 left there and an x squared left there. So now we're back in the situation we like, the product of real quantities being 0. That means one of those had to be 0. So either 6x cubed is 0 or 6 minus x squared is 0. 6x cubed being 0 means x is 0. And this other one means x is plus or minus square root of 6. And you notice that we want exact answers. That's part of the beauty of calculus. So we do not go and put this into a calculator or anything like that. So these are the places where f prime might change sign. So what I like to do now is put those on a number line. So I'm going to put mine minus root 6, 0, plus root 6. And over here I've got f prime and f. And since, unless we messed up here, these are the only places where the derivative could possibly change sign. In other words, if I find out that at some number way out here, who knows what number it is, f prime is, let's say, negative, then I know f prime is negative all the way from negative root 6 forever to the left. Because there's no more places, other than these three, where f prime could possibly change sign. That's going to be wonderfully helpful for us. So I want to pick a number out here, and a number here, and a number here, and a number here, and figure out if f prime is positive or negative in each of those four regions. And just from those four numbers, I'm going to know what f prime is everywhere. So let's give me a number out here. This is negative root 6. So let's suppose that we want to look at f prime of negative 3. And the nice thing is we don't even need to know the actual number of f prime of negative 3. We don't need to know the value that it equals. All we need to know is whether it's positive or negative. So I'm just going to write out here the sign of f prime of negative 3 is what? We have two things we could plug it into. We could plug it into this. That's going to be a lot of work. Or if you plug it into the factored form, it's very little work at all. Because again, I don't care about the actual numbers. I only care about the sign. So if I plug negative 3 into 6x cubed, a negative cubed is going to give me a negative. And 6 times a negative is going to give me a negative. So I'm going to denote that by saying I got a negative from there. When I plug negative 3 into this, I get 6 minus 9. That's another negative. So I got a negative times a negative, which is positive. So by picking a number out here, I figured out that f prime was positive at that particular number. We've already decided that the only places where f prime can possibly change sign are these three. So as long as I don't cross over into this region, f prime is positive. All of those numbers out there, no question. So what does that tell us about f? F is doing what? F is increasing all the way from negative infinity to negative root 6. And we got that just from plugging in the one number. That is a lot of power. That's part of the power of calculus. All right, let's make sure we understand this. Let's pick a number in here. What would be a good number to pick there? How about negative 1? So when I plug negative 1 into my factored form, a negative cubed is still a negative, times 6 is a negative. But when I plug negative 1 into this, I'm going to get 6 minus 1, which is 5, which is positive. So now I got a negative times a positive, which is a negative. So again, that tells me that every number between here and here, f prime is negative. So what is f doing that whole way? F is decreasing. Let's keep going. Pick a number here. Let's pick 1. And of course, there's infinitely many choices you could pick here, right? I could pick 1 here. I could pick 2. I could pick 1/7. I could pick 1.395. Just have to pick one number. So now I'm plugging a positive 1 in and I'm cubing it. And when I do that, I get a positive. So that the sign for the first term is positive. And then 6 minus 1 squared is still 5. That's still positive. So I get positive, positive, which is positive. So between here and here, f prime is positive, meaning f is doing what? F is increasing all that way. And by the way, on the homework, this is the sort of work that we want you to show. On the homework in the exam, take your derivative, set it to 0, find these places, draw a number line, indicate over here what numbers you're plugging in so that we know that you really understand the process. You're not just copying it from a calculator or a computer or something like that. We need one more number out here. So how about we choose 4? 6 times 4 cubed, that's definitely going to be a positive. And 6 minus 4 squared, that's 6 minus 16. That's a negative. So we got a negative. So what's f doing out there? F is decreasing. And now we've answered our questions. So we can say, so f is increasing on what intervals? All the way from negative infinity to negative root 6. Incidentally, we never put brackets, the square ones, with infinity or negative infinity, because since they're not actual numbers, they of course can't be included in the interval. F was increasing there. F was also increasing here between 0 and root 6. So and on the interval from 0 to root 6. And we also know that F is decreasing F was decreasing where F prime was negative. So from negative root 6 to 0. And then again, from our chart there, all the way from positive root 6, all the way to infinity. So now we know exactly where the function is increasing and decreasing. But we want to figure out everything we can possibly figure out about this graph. So not only, if you think about our chart for functions, we look at where they're increasing and decreasing, but we also look at where they're concave up and concave down. So that's going to be question C. Where is F concave up? Where is F concave down? And now we have to think back to our chart. What does F concave up mean? F concave up means F prime is increasing. But it's hard to just look at a function and decide if it's increasing or decreasing. That's what we just discovered. It's easier to look to see if the derivative is positive or negative. So F concave up is the same as F prime increasing, which is the same as F double prime positive. And then F concave down, according to our chart, is where F double prime is negative. So we're going to want to look at the sign of F double prime in order to figure this out. So let's remind ourselves about what F prime was. F prime was 36x cubed minus 6x to the 5th. So let's try to figure out what F double prime is. F double prime is just the derivative of this. So by our constant multiple rule, the 36 stays there, and our power rule says the 3 comes down. So we get 36 times 3, which is 108. And then we reduce the power of the exponent by 1. Then we do the same thing here, minus 30x to the 4th. And again, you could now try to set up some sort of complicated inequality and set this greater than 0 and then try to set it less than 0. It's quite difficult to solve these inequalities. You can try it on your own if you don't believe me. But instead, let's figure out, just like we did with part B, where this instead is 0. So I hope you're convinced by now that we should not do any dividing at this point. We should instead factor. So what can we factor out of both of these terms? I think they both have a 6x squared in them. 18 minus 5x squared. So we've got a product equaling 0. One of the pieces has to be 0. So we could have 6x squared equals 0, or 18 minus 5x squared equals 0. 6x squared equals 0 means x is 0. Or here, if I bring the 5x squared to the other side and then divide by 5, I think I get x squared equals 18 over 5, which is 3.6. So x equals plus or minus square root 3.6. So these are the 3 places where what might happen. These are the 3 places where F double prime might change from positive to negative. Meaning those are the 3 places where F might change between concave down and concave up. Well, we want to figure out if it actually does that. So we do the same thing like we did in part B. We'll draw a number line. And I want to be able to decide if f is concave up or concave down in each of these intervals. And in order to do that, I want to figure out if f double prime is negative or positive. So we're going to have to pick some points again. So we'll pick a point on the left of this. How about -2? And we don't really care about the actual value, right? We just care about the sign. So let me write sine of that. And again, it's up to you whether you want to plug into the factored form or the unfactored form. But since we don't care about the actual number, the factored form is going to be much easier. In fact, no matter what I plug into this first part, other than 0, which I know I'm not going to plug in because I'm picking numbers on either side of 0, 6x squared is always going to be positive. So the first sign here I'm always going to be writing is a plus. And now if I plug in -2, -2 squared is 4. So I'm taking 18 minus 20, which is negative. So I get a positive times a negative, which is a negative. So now we figured out that f double prime is negative all the way from there to -infinity, right? Because the only places that f double prime could have changed sign are these three places. And if I'm going from here to the left, I don't hit any of those three places. So there's no chance that f double prime can change sign out here. So if f double prime is negative, what does that tell us about the concavity of f? It is concave down. Good. Let's pick a number between here and here. So the sine of f double prime of -1. Again, 6x squared is going to be positive no matter what. But when I plug in -1, I'll get 18 minus 5, which is a positive. And the product of two positives is positive. And if f double prime is positive there, we know that f is concave up. You'll find this all much more exciting when we're doing these real-world problems about saving people's lives and saving money and saving the environment. All right, so what have we noticed? In the part B, every time that I moved from one region to the next, the sign changed, right? We went positive, negative, I think is what we went. And here, we've gone negative, positive. So are we just wasting our time in checking the next region? Is it always going to change sign? Let's see. Let's plug in 1. 1 squared is positive. 18 minus 5 is positive. So here we got positive times positive, which is positive. So here's the first example of why we can't just plug in the first interval and then assume that the sign is going to change every time. Because here it didn't change, right? We got a negative, a positive, and then another positive. And you can even understand why that happened, because if you think about the graph of 6x squared, right? This is the term that gave us the solution of 0. What does the graph of 6x squared do when it hits the x-axis? It comes down, it hits the x-axis, but it doesn't cross through the x-axis. It actually bounces off the x-axis and doesn't change sign. You can contrast that with what we had in part B, where I think we had an x cubed out front. And what does the graph of x cubed do when it hits the x-axis? It hits the x-axis and then goes to the other side. So it does change sign here. So because this was an even power, we could have known that we were not going to change sign at 0 here. Let's pick one more number out here. How about 3? Again, anything squared is going to give us a positive. 18 minus 5 times 9, right? If I plug in 3 there, I get a 9. That's a negative. That's a negative. Concave down. So what is our conclusion about the concavity? F is concave up all the way in here. So on the interval from negative square root of 3.6 to positive square root of 3.6. And f is concave down all the rest of the way. Negative infinity on the interval. And from square root of 3.6 all the way to infinity. Again, this is the sort of work that we would like to see so that you earn full credit on an exam or a homework problem. All right, we're almost done with this problem. It's a long problem, I know. D is going to be having us sketch the graph of f. And we're going to show all the different things that we have found in the first 3 parts of this problem. So let's just remind ourselves what we did. In part A, we found that we had roots at where? X equals 0 and x equals plus or minus 3. Those were our roots. In part B, we made a number line which had the numbers negative square root of 6 and 0 and square root of 6. And we did our f prime and our f. And we figured out that the signs were changing every time there. So that's what f was doing. So this is just a recap of those parts. So now let's try to draw our graph. Part A, we know that we touch the axis in 3 places, at 0, at negative 3, and at positive 3. Part B tells us we are increasing all the way from the left of negative square root of 6, right? So all the way from negative 3, we're increasing. So if we're going to be increasing all the way from negative infinity, and we're going to hit this point, should I start above the x-axis or below the x-axis? The only way I can be increasing and hit this point is by starting below the x-axis. So I'm starting down here, coming up like this. And where's the next point when something interesting happens? Is it negative square root of 6 or negative square root of 3.6? Negative square root of 6 comes first. So here we are at negative square root of 6. And what changes there? Our function now starts to decrease. But we're still concave down because we haven't gotten to this other point yet, negative square root of 3.6. So for this next little interval here, f is supposed to be decreasing, but still concave down. And remember, decreasing concave down is the one that looks like that. So we were concave down all the way so far. Now we're going to hit, what do we call that when we change concavity? We call that an inflection point, right? So now we're going to be concave up, but we're still decreasing. And we know we've got to hit a root at 0. So now we're concave up. So this is an inflection point. Concave up and decreasing. The next point where something interesting happens is at square root of 3.6. And after that, square root of 6. So you'll notice we're still concave up, but now we are increasing. So concave up increasing looks like that. We're almost done. What happens the rest of the way? We're concave down forever, but we're still increasing until we get to the square root of 6. So concave down increasing looks like that. I think if I were drawing this graph a little bit better, it would be perfectly symmetrical around the y-axis. And now the rest of the way, we are concave down and decreasing, and all we have to do to make sure we get the right graph is to hit this root at positive 3. So concave down, decreasing, like that forever. And there's really nothing else you would want to know about this function. You know where it's increasing, decreasing, concave up, concave down, where the roots are. This is everything there is to know about this graph. And we got it all through the power of calculus. And later on this semester, when we have these sorts of things in word problems, we'll apply the same ideas to figure out where graphs get to their high points and their low points. But for now, we have a check your understanding so that you can practice this on your own.